So hello and welcome to today's lecture recap. And as usual, I'm going to start with a quick review of what we talked about last time. And so that was basically various applications of our thermal radiation formula, telling us the total power of radiation coming off an object at a certain temperature. And what we did was we combined that in various situations where you have some incoming power, some incoming heat per unit time, and some outgoing power because of the radiation, and we have a steady state situation, what we're able to do in that case is predict the temperature of our object. And a very interesting application was to predict the surface temperature of a planet. And so I'm going to go over that shortly, but I wanted to actually start with a quick clicker question just to make sure that a certain very important concept is kind of solidified for you. Okay. So the question is, if we think about our solar system, we think about the power from solar radiation that's hitting the Earth. The question is, what would happen if we take the Earth and move it twice as far away from the sun as it is now? So think about that, and then we'll come back and discuss it. I'll go and get some more paper. All right, here we go. So I'll draw a picture. And so the idea is that we think about the sun, we think about the Earth, and then there's this alternative where the Earth is twice as far away. And so the point of this question is that the Earth isn't really changing the size. And so what's important here is really the intensity of the solar radiation. So the thing that's different is this power per unit area. At the location of the Earth, that power per unit area is what we call the solar constant. We calculated it last time. And basically the difference, if we're much farther away, is that the intensity of radiation is going to be less. How much less? Well, the logic is that the sunlight expands out uniformly in all directions. And so the power per unit area is equal to the power of the sunlight divided by the total area of that sphere at a radius r. Okay, so that's 4 pi r squared. If we think about the Earth moved twice as far away, then the sunlight would now be spreading out over the whole surface of a sphere, which has twice the radius. And so instead of 4 pi r squared on the bottom, we're going to have r replaced with 2r. And so the intensity, so this is our intensity, is going to be replaced with the intensity over 4. Okay. So because the sun has to spread, the sunlight spreads over an area which is 4 times larger, then the intensity or power per unit area is going to be 4 times less. Okay. And so the answer to this question is that the power of solar radiation hitting the Earth would be 1/4 as much as before. Okay, so that's really important, this kind of 1 over r squared proportionality, that if I double the distance, I divide the intensity by 4. Let me just give you an extra explanation, basically the same idea, but just expressed in a different way in case it's helpful to you. This was the explanation from the class last time. And so the idea is, if we want to think about this power per unit area, what I could imagine first is that there's a certain area, And I think about that area as a certain fraction of the entire sphere at a distance r from the sun. Okay. So if you have an object with sort of cross-sectional area A, then the fraction of the sunlight that will hit that object is like the fraction of the sunlight that would get through a hole with area A taken out of an entire sphere whose area is 4 pi r squared. Okay, so that fraction is A over 4 pi r squared. The power going through the hole is the power of the sun times this fraction. And then if we want to calculate the intensity of the sunlight at this location, we divide that power by the area. So the area then cancels out, and we find that the intensity is equal to the power coming out of the sun in joules per second divided by 4 pi r squared. It's the same formula that we had just before. Okay, and again, if we double r, then we're going to take intensity and divide it by 4. Okay, so for our application, the first thing we were interested in was predicting the surface temperature of the Earth. And in that case, if you evaluate the power of the sun divided by 4 pi times the distance from Earth to sun squared, you end up getting 1,367 watts per meter squared. And that's what we call the solar constant. Later in today's class, we're going to consider a similar calculation, but for Mars. And so we'll need to understand how this intensity changes in that case. Okay. So let's review our calculations from last time where we predicted the surface temperature of the Earth. And our basic setup is that we have sunlight coming in. Some of it's absorbed by the Earth. That's what's called H in, the amount of sunlight, the amount of power, or sorry, joules per second, I guess that's a power of solar radiation absorbed by the Earth. It's called H in. Okay. If we're in a steady state situation where the temperature of the Earth is not changing on average, which is true because the Earth has been in the solar system for quite a long time. So there's a constant surface temperature, and so we'll have a power of radiation going out that would be equal to the power of radiation going in. Okay, otherwise the temperature of the Earth would be changing. Okay, so this is our basic setup, and then we write the various expressions. So the power going out is coming from the usual thermal radiation formula. It's AE sigma T to the fourth. For the area in that case, we're talking about the entire surface area of the Earth, because the Earth is more or less radiating uniformly in all directions. If you think about the Kelvin temperatures at different points on the Earth, they're fairly similar, and we're just basically defining this parameter T to be something like an average temperature that we can use to model the whole planet as a uniform temperature object. Okay, so that's a simplifying assumption in our model. Okay, so that's the outgoing radiation. The incoming radiation is based on this solar constant, so the intensity of sunlight at Earth. We need to multiply that by the area that the Earth cuts off as the sunlight is coming towards the Earth. There's a certain area that the Earth cuts off, and we understood last time that that was basically the area of a disk. What's important is not the surface area of the whole Earth, or even the surface area of half the Earth. It's just the disk, the area of the disk that the Earth takes up. Comparing it to this previous slide, that's the area that would be missing from the sphere. That's the area of that entire 4 pi r squared where the sunlight would actually be hitting. Okay. So we multiply the intensity by that pi r squared, where the little r is the radius of the Earth. And then the last thing we have to take into account is the fact that some of that radiation actually doesn't really hit the surface of the Earth. There's some fraction of the radiation that bounces off the clouds or the atmosphere. And so that's indicated by these yellow arrows going out. And this quantity we defined last time, the albedo, is the number that tells us the fraction of the radiation that's reflected. Okay. So because we want the amount that's absorbed by the Earth, what we take is this intensity times the area, and then times 1 minus A, which is the fraction that's actually making it to the surface. So we have an expression for the outgoing power. We have an expression for the ingoing power. We assume that there's a steady state where we've reached some equilibrium temperature. And so we set H in equals H out and solve for T. So this was our result. And then we plugged in some numbers and we found something very interesting, which is that if you take the emissivity to be 1, which is the emissivity that we would have actually if there's no atmosphere in the planet. So if we had the Earth and we just looked at what is the emissivity for infrared radiation for the rocks and ocean and plants and so forth, then we would end up getting something like emissivity 1, very close to 1. The temperature, if we plug everything in then, is minus 18 degrees Celsius. So it's quite a bit colder than our actual temperature on Earth. The reason why it's not an average temperature of minus 18 degrees Celsius is because of the greenhouse effect. And that was basically just what's going on in this picture here. So we have this atmosphere. The atmosphere contains what we call greenhouse gases. And the effect of those is that they absorb some of the infrared radiation coming off the surface of the planet. So instead of going straight out into space, what happens is that energy goes into the gases, and part of it goes forward and part of it goes backward, back to the surface of the planet. And so effectively, we're going to have less radiation coming out of our planet. Okay. So effectively, we have an emissivity, which is less than 1, so 0.6 turns out to be the correct value. Okay. And so if you plug that number in instead of E equals 1, then you get a temperature of 14.5 degrees Celsius, and that is much more realistic for the actual surface temperature of the Earth. Okay. So the greenhouse gases are kind of helpful in that our temperature is not minus 18, it's more like 14.5. But then the reason why people are worried about greenhouse gases and then about global warming is because if we keep adding carbon dioxide into the atmosphere through this human activity, what we would then expect to happen is that the emissivity would go down further as this effect becomes greater, and we would end up with a rising surface temperature of the Earth. Okay, so that's what everyone is concerned about. Let's have a question to think about now. And so in this question, we're going to think about the same situation. This is a question, I think, from one of the previous midterms. Same situation, except instead of Earth, it's Mars. And so what I want you to do is think about not the entire question, but specifically, what is the expression that we should use for H in for Mars? What are the things that are different from the case of the Earth? And so let me give you a couple minutes to think about that, or just pause the video and then I'll talk about that. Okay. So let's start from the expression that we had for the Earth. So we have H in equals A times sigma times, that's not right. I'm writing the wrong one. That was the expression for H out. So we want H in. So we said that was the solar constant. So this is the Earth. H in for the Earth, it was the solar constant times pi r squared times 1 minus the albedo of the Earth. And now we want to know what's the answer for Mars. So it's kind of obvious. It's really just the same equation, except instead of the Earth quantities, we write the Mars quantities. Now, if we refer back to the question, so it gives us the albedo for Mars, gives us the radius of Mars. Okay, so it's important that this is not the distance of Mars to the sun. This is just the radius of the planet itself. That's what's important for figuring out how much of that solar radiation is going to be absorbed. And then finally, in the question, it does not give us the intensity of sunlight at Mars. Okay, so this is like the interesting part of the question. And what we can do there is look at what it gives us. It gives us that the solar constant at Earth is 1367 watts per meter squared. And it gives us that the distance from Mars to the sun is 1.52 times the Earth to the sun distance. So R Mars equals 1.52 times R Earth. Okay. So drawing the picture there, this is our Earth, this is our Mars, and so it's larger. And earlier in the class, we understood how to deal with this. So we said that if you double the distance from the Earth to the sun, then you're going to get 1 over the square of that, so 1/4 of the intensity. Now, Mars isn't actually double the distance to the sun. It's 1.52 times the Earth-Sun distance. And so what we do is we take I Mars, and we can just take the solar constant and divide it by the square of 1.52 squared. Okay, and so that's again based on the idea that, I is equal to the h of the sun divided by 4 pi r squared. So in terms of proportionality, we have that I is proportional to 1 over the square of r. Okay, and so that means that if you multiply r by a certain factor, then you just multiply I by 1 over the square of that factor. Okay, and so that's what you need to do for this question. So we write I Mars, I solar constant over 1.52 squared, and then the other things you just read off from the question, and then you're done. Okay, this is actually an interesting question to have today, because apparently Mars is right now about as close to the Earth as it gets today or tomorrow. I was reading that it'll be the brightest in the sky that is going to be anytime in the next 10 years. So have a look if you want to find Mars. Just go outside. I think wait a couple of hours after sunset, and then look towards the east, and you'll see a very bright red object in the sky, reddish, an orangey-ish reddish star. Okay, so that is it for our discussion of radiation for now. We're going to move on to a new topic, and the new topic has to do with basically making thermodynamics work for us. So we're going to talk about applications where adding heat and removing heat from various systems is actually going to be useful in building things like engines or refrigerators or all sorts of other interesting mechanical devices. And the key thing here is that we're going to be focusing on gases, and we're going to be thinking about adding energy to gases when we don't necessarily just keep the volume of the gas constant. Okay, so what we've understood so far is that if I add energy to a system, then, well, we could have a phase change. If there's no phase change, then the temperature increases, and we have that Q equals mc delta T. But there's a more general situation which can happen where you don't necessarily keep the volume of your gas fixed. Okay, so we understood that if you do keep the volume fixed, you add energy, temperature goes up, and the pressure goes up. We talked about that in the context of the ideal gas thermometer. But what that can do is actually lift objects. So if you allow part of your container to be movable, then that increase in pressure can actually lift a weight up to a higher height, and so we can use that for various technological applications. What I want to do today is mostly just think about the origin of that force that's going to be generating the pressure. So the origin of this pressure that will allow us to do work and lift objects and run car engines and all of that. So I want to go back to this molecular picture where the force produced by a gas, or the pressure produced by a gas, is really due to all these collisions of the gas molecules with the walls of a container. And so what I want to understand is, how big is the force going to be for a certain collection of gas molecules with certain microscopic properties? Okay. This is what we want to derive here. And so I want you to take a few minutes to think about this, staring at this picture and thinking about what sort of microscopic properties of these atoms in the picture could I vary that would have an effect on the force or the pressure on the wall. Okay, so think about that a little bit, and then we'll talk about it. Okay, so we had a good discussion in the class today, and people identified various aspects of this picture that we could modify kind of at the molecular level that would have an effect on the pressure. Okay, so one of the things that people talked about is that you could imagine just having less molecules there. So I can imagine that picture, but half of the molecules would be absent. What that would mean is that we could say that the density of molecules, or more specifically, like the number density, the number per volume, that would affect the pressure, because if you had less molecules per volume, then you're going to have less collisions, and so it's going to be less of a force on the wall. Okay, so that was one thing. So that would be affected if you had a big container and you changed the volume of the whole container, or you added more molecules to the container. Those things would affect the number density. Okay, so we can think of really, the total number of molecules, the volume, but at this microscopic level, what's important is just how many molecules are there per unit volume. So the number density. Another thing we could change is the actual, like, what kind of molecules are they? So the mass of these particular objects is going to affect how much, like, impulse, that's I guess the correct technical term, but the impact for each collision is going to depend on the mass of the molecules and also on their velocity. So mass of these molecules is something that will affect the pressure. I could take the same set of molecules with the same velocities. If their masses are bigger, you're going to have more force and more pressure. And then finally, the velocity. If you have molecules and they're moving faster, then actually, number one, there are going to be more collisions per time. Number two, each collision is going to have more impact. And so there's really two separate ways that changing the velocity is going to change the force overall per unit area on the wall. Okay, I think we talked about that in a previous class. So the extra part here is just to be a little bit more quantitative about how these various quantities will change the pressure. And so let's just go through those things that I mentioned. Number one, we could imagine changing the density. And I kind of already indicated that if I had, say, twice as many molecules here as I did in this picture, then we're going to get twice as many collisions per unit time. And if I keep everything else the same, that'll just lead to twice as much pressure, twice as much force per area. Okay, similarly, if I double the mass of these molecules, then that turns out to, so what it really does is it doubles the momentum of these individual molecules. And then when you have a collision and the momentum reverses, then you're going to double the change in momentum associated with each collision. Okay. So the force of the molecules on the wall is actually directly related to how much change in momentum do I have for each collision and the number of collisions per time that I have. Okay, so it turns out that doubling the mass basically doubles the change in momentum that you have with each collision, and that ends up doubling the force and doubling the pressure once we divide by the area. And then the final thing I already kind of mentioned, that doubling the speed of these molecules, or the magnitude of the velocity, that has the effect of, number one, causing twice as many collisions per time because everything is happening twice as fast. And number two, again, that will double the momentum. And so it'll double the change in momentum per collision. And that means that we're also going to double the force because of that effect. Okay. So we have these two different effects where doubling the velocity for two separate reasons. We have a doubling of the pressure. And so overall, the pressure is going to be proportional to the square of the velocity. Okay. So summarizing everything that we've learned from this microscopic picture, we can say that the pressure of these molecules on the walls of the container is going to be proportional to the density, proportional to the mass, and proportional to the square of velocity. And then there would be some proportionality constant out front of everything that we would have. And we'll talk about what that constant is shortly. Okay. So there's one interesting thing that you might have noticed in this formula, and that is that this combination that appears here, the mass of the molecule times the average speed of the molecule squared. So this thing is directly related to the kinetic energy of those individual molecules. And previously in the course, I suggested that the kinetic energy, the average kinetic energy of molecules in a substance, is directly related to the temperature of that substance. Okay, so let's kind of formalize that now. And I'm going to propose to you a different definition of temperature that's based directly on this microscopic picture. Okay, so let's say that temperature is defined to be equal to this average kinetic energy per molecule. Okay, the average kinetic energy of the molecules up to some constant. So maybe in some units it's equal, in other units there'd be a constant out in front. Okay, so let's make this basic assumption that if we double the average kinetic energy of the molecules, that we're doubling the temperature. Okay. So if we make that definition of temperature, and then we go from this formula here, what we can do then is replace half mv squared with the temperature times some other constant. Okay. So then our formula becomes this one right here. Okay, and I'm not yet worrying about exactly what these constants are. What the molecular model has taught us is that the pressure apparently is equal to the number density, the number per volume, times the temperature. Okay. And this thing is something that we kind of understood earlier. Okay, so this thing was actually our previous definition of temperature. Remember, when we defined the Kelvin scale, we said that we're going to define temperature to be equal or to some constant times the pressure for a set of gas molecules at constant volume. What we find now is that if we make this other definition of temperature, temperature equals the average kinetic energy of the molecules times a constant, then that leads to the same result, that pressure is proportional to temperature. Okay. So we kind of have these two definitions, one based on an ideal gas thermometer, the other based on a microscopic property of the molecules, and they turn out to be consistent with one another. Okay, so those are actually two different ways that you could define what we mean by temperature. Finally, I want to talk about this constant here. Once you have this relation, you can just go out and do an experiment and figure out what the constant is. So it should be the same for any setup where you can choose different numbers of molecules, different volumes, different temperatures, and you should always find this relation, this proportionality between pressure and the other quantities, and this constant should be the same in all situations. Okay, and this turns out to be true, and we therefore just give this constant a name and assign a value to it based on our experiments. Okay. And so the name we give it is either little k, but you're probably more familiar with a different definition where this constant is called R divided by Avogadro's number. So this constant turns out to be 8.31 joules per mole per Kelvin divided by 6.02 times 10 to the 23. And if we then take that, so this is just like R divided by Avogadro's number is just what we're calling that constant. Let me show you then that the final output of all of that is that we have derived the ideal gas law. Okay, so far we said that based on the molecular model and based on our molecular definition of temperature, we learned that P is equal to some constant times the number of molecules divided by the volume times the temperature. And now I'm telling you that we're just going to call this constant R divided by Avogadro's number. Okay, and then we could just go out and measure what R is, and it turns out to be 8.31 joules per mole per Kelvin. If I rewrite that formula, then what I have is P is equal to R divided by V, and then N divided by Avogadro's number, and then T. And we recognize this thing as N, which is the number of moles. Okay, and so finally, if we rearrange everything, what we find is that PV is equal to N, the number of moles, times R times T. And I think all of you have seen that many times in the past, probably in high school chemistry, maybe in high school physics. So probably all of you are quite familiar with this ideal gas law. So the way I like to think about this is kind of as an equation that allows you to predict how much force a gas is going to exert on the walls of its container. Okay, so I like to think of temperature and volume and the number of moles as being the input. And then this equation then predicts how much force that we're going to have on the various walls, or the more precisely, the amount of force per area. Okay. So that's it for today. We have a very exciting demo at the start of next class that I didn't get to today. Let me just give you a quick preview. So the demo does not involve a Rubik's Cube, but it does involve a bottle of wine, a candle, and a fancy wine glass here, not my coffee cup. And so it looks like it's going to be a very romantic demo at the beginning of next class. So definitely tune in for that, and we will see you on Friday. Good luck with the midterm, everyone.